We're now going to look at how we can make alkynes. We call making particular substances the synthesis. So this is going to be a section discussing the synthesis of alkynes. The first reaction we're going to look at is called acetylide alkylation. Acetylide is the name for that negative ion. Alkylation means to add a carbon group to that. Our observed reaction looks like this. We start with a terminal alkyne. It must be a terminal alkyne. We treat it with sodium amide, as discussed above. That would deprotonate it. And then we treat it in a separate step after we've allowed the sodium amide to completely react. We treat it with an alkyl halide, which we symbolize as carbon group attached to X, X being our symbol for a halogen. It should be noted that the carbon group should either be methyl or a primary carbon group. And the reason for this is that we need it to be a very good SN2 substrate. The result of the reaction would be that the hydrogen that is attached onto the terminus of the alkyne is replaced with the carbon group of our alkyl halide. We can see the mechanism for this below. We start with our terminal alkyne. We treat it with sodium plus, acetylide minus. Sodium is basically a spectator. We treat it with sodium plus, amide minus. The sodium is basically a spectator. The amide ion is a very strong base. It comes over and it makes a bond to the terminal alkyne hydrogen. The hydrogen lets go of a pair of electrons on the other side, which goes onto the carbon of the alkyne. So we get an acetylide ion paired up with sodium, and then we also get a molecule of ammonia. This species right here is a very strong nucleophile. So if we then put in an appropriate SN2 substrate, the lone pair of the acetylide ion will come over, make a bond to the carbon group, and push out the halide ion on the other side. Classic SN2 reaction. And we'll be left with our desired product. These two steps are summarized below. Another way of synthesizing alkynes involves what's called a double elimination reaction. It's called this because what we're going to do is essentially an E2 elimination reaction 2 times. When we do an elimination reaction 1 time, we make a pi bond, and that makes an alkene. If we do an elimination reaction a 2nd time on the same 2 carbons, we would make a 2nd pi bond, and that would make the molecule an alkyne. There's 2 different observed reactions for this. They use basically similar or identical reactants. However, the reagents are a little bit different, and the outcome is a little bit different. The first one involves using a substrate, a reactant, that has adjacent halide or halogen atoms. We call this a vicinal dihalide. The halides typically are chlorine or bromine. We learned how to make these last semester when we looked at addition reaction of alkenes. If we take this and treat it with potassium hydroxide, which is a medium strength base, we can get an alkyne, we can get double elimination. However, in order to get the second elimination to work, we have to heat it up to a pretty hot temperature, 200 degrees C. The result of this is going to be an alkyne. But it turns out under these conditions, no matter where we have our vicinal dihalide, the alkyne is going to begin to move around in the molecule. And so what we're going to be left with is a mixture of the possible internal alkyne regioisomers. Another set of conditions uses a much stronger base, the sodium amide that we talked about earlier. We're going to use that in excess. So in other words, in theory, it should take 2 equivalents of base to accomplish this reaction, since we need to remove one and then a second hydrogen. We're going to put in more than 2 equivalents. We're also, after the first step is over, we're going to put in aqueous acid, which we symbolize with hydronium ion, in order to stop the reaction and destroy all of the strong base. The result of this is going to be production of a terminal alkyne. Again, regardless of where the 2 halides, adjacent halides are in the molecule is going to rearrange and give us a terminal alkyne. We'll see this in the mechanism below. Here's the mechanism of the reaction. We start with our substrate, and if we notice, our substrate has a halogen attached to one carbon, and then on an adjacent carbon, it has a hydrogen. So we have alpha carbon where the halogen is attached, and then beta carbon where the hydrogen is attached. This is terminology that we introduced when we discussed E2 elimination. We're going to put in our base. Our base could be amide ion or the hot hydroxide ion. The base is going to come over. It's going to deprotonate the beta hydrogen. The hydrogen is going to let go of a pair of electrons which are going to move onto the space between the 2 carbons. But in order to make room for it on this carbon, we push out the leaving group so that we don't form 5 bonds on carbon. This results in an intermediate which looks like this. It's an alkene that has a halogen attached to one carbon and a hydrogen attached to the other carbon. Again, if we look at it carefully then, we could say the carbon of the alkene with the halogen attached is the alpha carbon. The adjacent carbon would be the beta carbon, and there's a hydrogen available on that. So, base can come over. It can remove that beta hydrogen. A pair of electrons again comes in between the alpha and beta, and again, to make room, we push off the leaving group. This second step actually has a much higher activation energy. It takes a lot more energy to accomplish. So that's why we need to use either very strong base or a lot of heat to force this second step to occur. The result of this second step is formation of an alkyne between our original 2 carbons that had the halogens on them. However, under the base conditions, we get something occurring called a zipper reaction. I've put NH2-, but hot potassium hydroxide also will do this. We're not going to cover the exact mechanism of this, but what you need to understand is that if the alkyne is part of a longer chain, the zipper causes, through several steps, it causes the alkyne to move, changing positions on the chain. So the alkyne starts moving back and forth on the chain. Eventually, the alkyne is going to reach the end of the chain, forming a terminal alkyne. Now this turns out to be not favored, actually, as the internal alkynes have lower potential energy. However, because it's in equilibrium, they're constantly moving back and forth, and so eventually some of the molecules form a terminal alkyne. When the terminal alkyne is formed, if we are using amide ion, the amide ion is going to very rapidly deprotonate that. As we discussed, that's a very favored reaction. So we make a molecule of terminal alkyne, it becomes deprotonated, it becomes an acetylide ion, and essentially once it is deprotonated, it's never going to go back. It's never going to be able to do the reverse Bronsted-Lowry acid-base reaction because the equilibrium so strongly favors deprotonation. That means that the activation energy for the reverse reaction is going to be very large, and it won't be able to go back up to this. Now, the result of this then is kind of interesting. It takes advantage of what we understand about Le Chatelier's principle. If we imagine that this portion, the zipper, is setting up an equilibrium where we're making a whole bunch of different alkynes, including a very small amount of this alkyne. When we make this small amount of this alkyne, it gets deprotonated and converted to something else, which makes it unavailable to go backwards in the equilibrium, and also puts a pressure on the equilibrium, pulling additional molecules down to try to replace it by Le Chatelier's principle. In Le Chatelier's principle, if you have an equilibrium and you remove a molecule from one side of the equilibrium will shift in that direction to try to replace that molecule that was removed. I often call this the 99 molecules on the wall because there's an old drinking song called 99 Bottles of Beer. 99 bottles of beer on the wall, 99 bottles of beer. Take one down, pass it around, 98 bottles of beer on the wall. The idea here is that we have 100 molecules in this equilibrium. If we deprotonate one and take it away, now there will only be 99 molecules. Eventually one of those molecules will be converted to a terminal alkyne. It will be deprotonated and taken away. Now we will have only 98. This process should continue as long as we have base to deprotonate. So if we have an excess of base so that we can deprotonate all of the products that are formed, eventually all of the molecules will have been converted to terminal alkyne and removed, and we will have 100% of our molecules right here. This can take some time, but after it's all done, what we can then do is just very rapidly put in aqueous acid. Aqueous acid is going to do acid-base reaction with the acetylide. The acetylide will reach out, grab a hydrogen, and that will result in formation of the terminal alkyne. Therefore, this reaction has two different regiochemistry outcomes. The potassium hydroxide conditions cause equilibration to internal alkynes. Internal alkynes are more stable. They have a lower potential energy than a terminal alkyne. A mixture of these internal alkynes, however, is produced. So if we look at this reactant, which is 6 carbons with a bromine on carbon 2 and a bromine on carbon 3, if we were to allow that to react with hot potassium hydroxide, we would most definitely form molecules of the 2,3 alkyne. However, because the alkyne can move up and down along the chain, some of these molecules are going to equilibrate and form the alkyne between carbons 3 and 4. These two products then are constitutional isomers of each other, and we would expect them in some kind of mixture. If we really needed the alkyne between 2 and 3, this would limit the usefulness of this reaction, because we would have to throw away some of our product. So this reaction works best in situations where there really are not isomers possible to be produced. The sodium amide conditions give a terminal alkyne. The terminal alkyne becomes deprotonated under the reaction conditions. As we discussed, we add in a hydronium step and protonate the acetylide that's formed. So at the end, we get essentially 100% of the alkyne between carbons 1 and 2. However, it should be pointed out that we get the alkyne between carbons 1 and 2 regardless of where the halogens were. So for example, in this example, the halogens are on carbons 2 and 3, but the alkyne is between carbons 1 and 2.